Howdy, howdy. We're going to talk about the over-up method as a way to calculate or graph the dilation factors in the horizontal or vertical directions. And before we do that, if you don't recognize this, if you can't tell that there's some kind of stretching going on in these, this is going by vertically by 2, this is going by horizontally times a factor of 3, but then vertically by a factor of 4. This is going vertically by a factor of 3. If you don't understand that yet, you may want to go back and watch my previous video because I'm going from the standpoint of you already understand what a stretch is. You just may not be able to tell how to put the stretch in the graph, or if you've got the graph, how to work backwards to figure out the equation. So we're going to be figuring out, if we have the graph, what's the equation and the stretch factors, the dilation factors, and if you've got the equation, how you would actually graph that without dragging out a graphing calculator. So, and also you should recognize these for sure. If not, you need to go back and watch an even earlier video to know what these parent functions are. So in this one, let's talk about over-up first. Okay, so over-up, this right here, my vertexes on all these are 0, 0. This is my quadratic equation, my y equals x squared. It's my formula here, which you should recognize. I don't have the points connected because I actually care more about the points. So from the vertex, this one goes over 1 and up 1. So over 1, up 1. I'm going to abbreviate with those and use. Now the next one, it's at 2, 4, but from that last point, I actually go over 1 and up 3. So over 1 and up 3 from the last point. Well, the coordinates are 2, 4 from the previous points, over 1, up 3. And then the next one's over 1 and up 5. And that pattern actually continues forever. So we're going from our vertex to our next point and our next point and our next point. And there's a pattern there that allows us to very quickly graph these without having to actually calculate what those numbers is. As long as I know where the vertex is, and it doesn't have to be here, wherever that vertex is, I can very easily graph the parent function knowing this over 1 up 1, over 1 up 3, over 1 up 5 pattern. So that's a simple way to graph. It's even simpler for our y equals absolute value function. It's over 1 up 1, over 1 up 1, over 1 up 1, over 1 up 1. So that is just over 1 up 1 all the time. Start at the vertex, work to the right, over 1 up 1, over 1 up 1. And then finally, we've got our square root function, our parent function. And so this is over 1 up 1, and then over 3 up 1, and over 5 up 1, which sounds kind of familiar, except it's exactly our parabola, except it's turned on its side. So over 1 up 1, over 3 up 1, over 5 up 1, and that pattern continues forever. So it's a very quick way for me to draw that. As long as I know where the end point is here, I can do that for the parent function. So the only thing there is, if I stretch now, I can use that basic shape that I know for the parent to apply to the stretch. So let me check my notes. What am I doing next? Yeah. All right, so these right here, I have these functions. I can tell that I've got a horizontal dilation of 3 because I know that's the pattern. It goes right there, and a vertical dilation of 2. Once again, if you don't understand that yet, go watch my previous video. So the parent function would be, it's a quadratic. It would be over 1 up 1, over 1 up 1, over 1 up 3, over 1 up 5. So I just apply the dilations. These are going to stretch by these factors. So instead of, for my over factor is 3, so I'd be, instead of over 1, I'd be over 3. So all those are going to be 3. And then here I'd be times 2, so that's going to be 2. The next one's going to be times 6, and the next one's going to be 2 times 5, or 10. So there's my new pattern if I was going to graph that. I'm not going to show that graph, but starting from the vertex, over 3, up 2, over 3, up 6, over 3, up 10. Same thing here. Horizontal dilation is definitely 5, and there is an invisible 1 out in front of there, which I can write in there. So my overs now are all going to be 5. And my ups are all going to be 1 still. Because for the absolute value, my parent function is 1, 1, 1, 1, 1, 1. So my new function is going to be over 5 up 1 over 5. It's going to be very, very shallow absolute value there. And then the last one here, once again, that's going to be my horizontal dilation. That's going to be my vertical dilation. Normally for a parent function, square root would be over 1 up 1, over 3 up 1, over 5 up 1. So in this case, it's going to be, that's going to be 2, that's going to be 6, that's going to be 10, and then these are just going to all be 4s. So that would be very easy for me to graph. Just go to wherever the vertex is. In this case, the vertex is still at 0, 0. But even if this thing had translated somewhere, this pattern, as far as where those points are going to land, relative to the vertex are all going to be correct. Okay, check the notes here. Next thing. Okay, continuing my worksheet. So back to where we were before. I've got this right here. I can tell it's definitely, I've got a new vertex. It's at 1, -5. That's my translation. I've got a dilation of basically 2, the vertical is times 2, and the horizontal, it's not over anything, but I'm going to say I've got a horizontal of times 1. So my over-up pattern here for the very first point, because our normal first point is 1, 1 here, and in fact that's all I really care about if I'm just doing the shape, it's going to be over 1 and up 2. So my vertex here is now at 1, -5, which is 1, -5 is right here. And so instead of going over 1 and up 1, and normally I would for the parent function, I'm going to go over 1, up 2. And then my next point, if I was going to do it, that next point would typically be over 1, up 3. So the next one, if I continue those out, my next one would be over 1 and up 6. So over 1 and up 1, 2, 3, 4, 5, 6. It would be right there. And then I'd have my partner points over here. So this thing would look roughly like that. All right, easy peasy. One more here. Once again, my translations, I've moved my vertex to -2, -1. My dilations in the vertical direction, it is 4, and horizontal is 3. So my over is 3 and my up is 4. I probably should have done those the other way around. That would be my first point. It's really nice for all of these. The very first point is over 1 and up 1 from the vertex. It only diverges after that. So start with my new vertex is at -2, -1, which is right here. And so I'm going to go over 3 and up 1, 2, 3, 4, and hopefully I'll get it right. And so the next point, if I wanted to draw it in, would normally be the pattern here is 1, 1, 3, 1, 5, 1. So the next point would be at times my horizontal times 3, so that would be at 9, and that would be at 15. Is that right? Except I'm using the wrong pattern. That's not the pattern for this one. This is an absolute value. It'd be 1, 1, 1, 1. So this is 3, 4 all the way across. Ignore that. So over 3 and up 4. So my next point's there. It would look like that. And then I'd have the same back in the other direction. Over 3 and up 4 would look like that. So that's how you do that. Okay, last thing here. One of the things this is really powerful is I can actually give you a graph and you can do the same thing in the reverse. Okay, so this one right here, definitely a square root. Our normal pattern for the square root is up 1 over 1, up 3 over 1, up 5 over 1. That would be the normal pattern for the parent function. In this case, I don't land at 1, 1, I land here. So I say, oh, I'd normally be there. I've stretched this out twice as much, so this is over 2 and up 2. So my dilations are 2, 2. So my horizontal is times 2, and my vertical is times 2. So my equation, I just calculate where my point is, -3, -6. So that's going to be x plus 3 and a minus 6 on the outside. It's a square root function, and I am over, my horizontal is 2. So that's that 2, and my vertical is 2, which is that 2. So this is, the equation is y equals that. So I can very easily look at the graph, especially for just the first point. That's all I really care about when figuring out these dilations. Now the only thing I haven't shown here is, well, what about if it's inverted? If it's reflected horizontally or vertically? Well, then you just have to think about the same thing. And like, okay, let's say these things were all flipped upside down. If they flipped upside down, the stretch is still going to be the same, except I'm expecting my first point to be here. Maybe it's down here, and then say, oh, it's it's still 3 and it's 1. I just have to go in the correct direction when I start graphing this thing. So it's always, where would that first point end up in the reflection of the parent function, and then just stretch it out appropriately. So you just have to know which direction you're going in when you start talking about reflections either across the x or the y axis. That's all. Ciao.